Hi all, I'm Dr. Clark here again, and today for general biology, we're going to continue with the topic of ecology and kind of pursue a little bit more into population ecology with population demography, and then we'll talk a little bit about community ecology. Okay? So first off, I want to talk about population numbers and kind of why we study populations and why we track populations. This is a really good example of the need to know what a population is doing um, before it's too late. Okay? So this is a passenger pigeon, a picture of the passenger pigeon, and um, in its height, there were at the peak of the population of passenger pigeons, they're the most abundant bird in North America. Currently, right now, the red-winged blackbird is the most abundant bird with somewhere around 2 billion individuals. It's thought that based on mark recapture and sightings and things like that, that the passenger pigeon at its height numbered somewhere around 9 billion birds. Right? And just the United States, just counts for the United States. Um, so that's the peak, and roughly 25 years later, the last passenger pigeon in the wild was killed. And so from basically a 25-year period, we went from 9 billion to 0. And there are many reasons for this. You can see here in this picture, hunting. So they were over-harvested by far. But also the deforestation that happened in the eastern part of the United States. Uh, Literally, there's very few sections in the eastern United States that have native trees, or I should say, trees that were native to the landscape when Europeans came and have not been replanted. So all the old growth forests in the eastern part of the United States are all gone, except for some parts in the Appalachian Mountains. But other than that, pretty much everywhere else has been clear-cutted, and these birds needed certain trees and certain canopy cover and things like that, and so they lost a lot of that habitat. So they had no nesting habitat, no food resources or little food resources, and extensive predation or extensive hunting pressure. And in 25 years, we eliminated the passenger pigeon from the wild. It took about another 10, 15 years before the passenger pigeon died in captivity, and they now are extinct. So from a population biologist point of view, that's an extreme case because we're talking 9 billion birds, the most abundant bird in North America, and in 25 years, humans have the capability of eliminating it from the planet. And so it's important for us to realize that with the right kind of pressure, with the right kind of um, disturbance in a given region, you can literally eliminate numerous individuals from the planet. Okay? So with that being said, we're going to start talking about some of those pressures, but also some of the ways that organisms can adapt to a changing environment. All right, so first of all, part of the reason why some organisms can withstand uh, changes to the environment better than others have to do with what we call life history adaptations. So life history is just describing the life cycle of an organism. So from egg or whatever it might be, seed, to juvenile, to adult, to death, kind of thing. Now there are two types of life history adaptations. You have species which we consider R selected species. Now these species grow really fast. They can typically withstand unsuitable habitats or changing habitats because they grow extremely fast and they can adapt fairly fast. So in unpredictable environments, R-selected species have a distinct advantage over K-selected species. K-selected species typically grow much slower. They need a more stable environment. Their reproduction is near carrying capacity at all times. So they're really, K-selected species are really stable. R-selected species are normally what we call boom and bust species. So their populations can explode and they shrink, and then they explode again and shrink. K-selected species are fairly stable. So they need a stable environment. Some other interesting pieces on selected species is, we can look at things like the age of at first reproduction. You would expect, if you're an R-selected, you're growing fast, you have early reproduction. K, you have late reproduction. Some other things, parental care. So are, the females or males taking care of their young? In R-selected species, there's normally very little or none. And in K-selected species, it's normally extensive. So that means that often K-selected species, because it's a stable environment, stable habitat, the young will stay with the parents for a long period of time and grow, and they don't have a lot of turnover. So their lifespan is long in K-selected species, and in R-selected species it's short. So here's a great example of an R-selected species. This is a species that can grow exponentially until it reaches the carrying capacity, and then it will be eliminated or die off to just a few individuals and then explode again. So the boom and bust of things like cockroaches. So you got a bunch of cockroaches here. The population is exploding, as you can see. There's literally millions of individuals here, and then eventually the food will be gone, or the water source will be gone, or something will take place, and the population will have to crash. Right? So they will grow at exponential growth, like we talked about before. So they have a J curve, but eventually that J curve becomes a sigmoidal curve, and they have to go into logistic growth because they will eventually reach the carrying capacity. It just happens to be that R-selected species often will overshoot the K by a long ways, and then they'll have a huge population crash. Maybe half of the population will die off, maybe even more, and then they'll start rebuilding themselves fairly quickly. Okay, so demography is really the statistical study of populations. So like the example that I gave at the very beginning with the passenger pigeon, we're interested in what's going on with a population over a period of time. Has it been growing for the last 5-10 years and now it's starting to decrease? Is it at its K? There's a lot of different things. How many individuals are within that population are adults? How many individuals within that population are juveniles? This is demography. This is what we do when we're examining populations. So we're not just doing it with humans. We know this information for humans typically. We can pick a country and we can determine, well, how many people are over the age of 60 in that country, how many are between 40 and 60, etc. And we've done that for a long period of time. Okay? And that's often why we collect things like census data, is to figure out those things for the United States, or other countries will collect their own kind of survey data. So the nice thing about that is you can predict what's going to happen to the population in the future. So let's say we examine something like Rock Springs, Wyoming, and we examine the population demography of people in Rock Springs, Wyoming, and we say, all right, well, we have this many kindergartners, this many kids between the age of 5 and 6, okay? and um, and we know that that's more than the number of individuals between the age of 14 and 15. Maybe it's double. That would suggest to us that in roughly 9-10 years, if nothing changes, those kindergartners are going to enter into high school. Okay? And if there are not enough spots, not enough seats in the high school to account for the children that are coming up, then you have to do something about it. Either build another high school, build some portable rooms so you can have classrooms, and maybe, basically trailer classrooms, things like that. But that demography, by analyzing that, we can tell what's going to be needed in the near future. Now, something might happen in between. You might have, half the families move away. Right? That's quite possible. Right? But that's why we examine it from a statistical point of view to figure out, okay, what's going to happen 10 years from now? Right? Or do we need a new high school? Right? Or are we going to be fine? Maybe there's only a few more kindergartners than there are high school students, freshmen. Then we might be all right. Right? But if there's double, then you might really need to think about building a new high school, or at least having some place to put those students, especially if you're at maximum. But we do this for all kinds of things. It's not just students, things like that. Roadways. Many of you have probably drove over the little clickers that are basically pressure sensors that click a number every time a car drives over it to let it know, okay, how many vehicles are driving on this road between this amount of time and this amount of time. Okay? And then they can start figuring out, well, do we need to put a stoplight in? Do we need to change the speed limit? Do we need to do road repairs? Okay? Do we need to increase the lane size? Okay? All of this is based on population statistics. You can do it from a human perspective, you can do it from an animal, a plant perspective, whatever it might be. That's how demography works, and allows you to predict things that you might need in the future. Okay? Now, many things that we're interested in population demography is whether or not the population is going to be growing. Okay? So if we know that the number of births outnumber the number of deaths, or the birth rate's greater than the death rate, then based on that, we would know that the population is increasing. If the death rate is greater than the birth rate, we know the population is shrinking. And we can also analyze that based on the age of the population and the sex of the population. So are there some countries where the number of individuals that are younger than 5, the death rate for individuals that are younger than 5, the deaths outnumber the births? In some countries, yes. So the population is shrinking, and it's because maybe they need better health care for young individuals. Maybe they need better nutrition for young individuals, these kind of things. So we can analyze it based on the age or the sex of the individuals across the world. So not just from a human perspective, but also from an organismal or animal or plant perspective. Okay. The other thing that you can do with demography data is you can group organisms, group individuals into cohorts. Many of you probably have been called, Generation Z, or Generation X, or I think the newest one, if you're born around 2010 or later, you're Generation Alpha, whatever it might be. Okay. sometimes people are called the millennials, these kind of things. This is a cohort of individuals. And this is just a way to group individuals that are in the same kind of age grouping or age pattern. Now, what does it tell you? Well, maybe it tells you what they've grown up with, what they've experienced in their life. So like millennials, in order to be considered a millennial, I don't think you can have grown up without internet or something like that. Maybe not without internet, maybe without computers or something along those lines. There's lots of stipulations. Okay, now one stipulation is you're just born. To be a millennial, you're born after the year 1980. Okay, to be a Generation Z, you're born after the year of 1990. Okay, to be a Generation Alpha, maybe you're born after the year 2010. I'm not entirely sure. It doesn't really matter. These are just ways to group individuals. As an ecologist myself, I group them based typically on age groups, and it depends on what species I'm interested in. If I can't age the species to a specific year, then maybe I'll just group them based on whether they're a juvenile or an adult, or maybe they're a second-year adult or something like that. Okay? If I can group them based on the actual age, like a lot of fish, you can age fish, so you can group them based on, okay, this is a fish that is less than 2 years old, a fish from 2 to 4, fish from 4 to 6, whatever it might be. Okay? But what that allows you to do is you can start looking at cohorts, and you can examine, well, is the birth rate for Generation Z different than the birth rate for Generation X? Okay? So is Generation X have a higher fecundity? So are they reproducing more offspring than Generation Z? By doing this, we can make that prediction again. We know that from 1950 to today, 2019, we've added about 6 billion people to the planet. Okay? So we know that growth rate. But then what if we're trying to predict out into the future? Are the Generation Z or millennials, are they reproducing as much as the Generation X? Are they producing as much as, the potential for alpha generation when they get old enough to reproduce? What's going on? So that's important, the fecundity portion. And mortality is also important. Is there a higher death rate in millennials than there are Generation X's, okay, or Generation Y's? What's going on? What's the mortality? What's the death rate? Okay, and has that changed over a period of time? Okay? That really allows you to define or examine a population's age. Do you have a bunch of old people in your population and very few young people? Are the young people, is there enough young people to replace the old people? And this is where we get into the idea of, things like Medicare, Medicaid, these different things that you might be paying into, right, to maybe reap the benefits after you retire, and maybe it's not going to be there, right? Because maybe there are more old people taking those resources than there are young people putting in money for those resources. And so population demography will allow you to figure out, well, at what time will that drain? What time will it be gone? And you'll either have to cut the amount that's paid, or all in all, you might have to cut the entire program. So that's ways at which we can predict what the future will look like by examining cohorts. The other thing that we can do is we can examine sex ratios. And this became fairly popular to examine in populations when we started figuring out that not all populations of birds are faithful or have a monogamous relationship. And we started figuring out that not only do birds often seek out other mates, but you can see this in the sex ratio. That often in birds, you'll see that more females are reproduced than males. And by examining that, when you see that there's a difference in sex ratio, then you can often find out, well, whichever the least amount of individuals there are reproduced, it's probably the least needed in a population. So if there's less males than there are females, then the males can probably mate with more females than one. Okay? The other thing can be true too, though. If there are more males than females, then maybe being male, maybe you're sexually dimorphic, meaning that you have different colors than females, maybe the male is really brightly colored, maybe being male is a disadvantage, and you're going to be predated on much more often than females. Okay? In the case of humans, the sex ratio is about 1 to 1. Now, there are more females on the planet than there are males, but that's because females live longer than males. Okay? But the birth rate or the birth ratio is basically 1 to 1. Age distribution, we already kind of talked about this. How many individuals in each age class are alive? Okay? And that kind of gives you an example of, well, what do you need to do to prepare for the future? Okay? All of this can be based and used, all this information can be used to create what we call a survivorship curve. Okay? And so this is really just kind of a general rule of thumb. If you're a certain species type, so if you're R selected or K selected, we can then break you down even further, the species even further, and give you some kind of survivorship curve. Either you're a type 1, 2, or 3 survivorship curve. And really it's just determining, well, at different age classifications, young, middle age, old age, what's your likelihood of dying, okay? Or what's the likelihood of surviving? Okay? And so for different species, it's going to be different percent of the population will survive those events, and that's what kind of type curve or how we calculate the curve. Okay? So again, 3 type curves. Type 1, so it has the highest mortality for the oldest individuals. So a type 1 curve, if you're born or you hatch in that or you germinate in that population, you're pretty much guaranteed to live until you get fairly old, and then that's where the most mortality happens. So survivorship is pretty even, and then a huge drop-off as you reach a certain age. A type 2, it's almost always the same. Okay? The mortality risk for small A or young, middle, and old is almost always the exact same. And then type 3, a massive crash, high mortality as a youngster, and then once you make it past that period, you have a fairly even or fairly low mortality rate until you get really old. Okay, so here's a good example of this. So for like humans or type 1, if you're born, for the most part, you have a high rate of survivorship all the way up until about 75 for men and about 78 for females, close to 80, depends on what country you're in. And then you have a pretty high crash rate and pretty high death rate after that. Kind of 75 is for males, and you start to see it tick down. 78, 80 for females, and you start to see it really crash. Okay? Hydra, which are kind of an aquatic cnidarian, it looks like a jellyfish that's upside down. They're type 2, so it's pretty much equal across their entire lifespan. But other things like birds have a very similar type 2. Most birds have a type 2. So if you're a robin, you might lay 4 eggs. 2 of them survive. Those 2 individuals pretty much have the same survivorship every single year until they reach their maximum age, and then they die. Oysters, insects, lots of plants, things that produce massive amounts of seeds or offspring will have a type 3 kind of situation where you have tons of offspring being produced. Most of them die. The ones that do survive, though, they do well. Their survivorship is pretty even or pretty good all the way until they meet their maximum lifespan. So you can also lump these into just kind of a rule of thumb. How many offspring are being produced? If there's very few offspring being produced and there's a lot of parental care, then you probably have a type 1. If there's a moderate number of offspring, okay, and some parental care, you probably have a type 2. If there's a massive number of offspring being produced and no parental care, it's probably a type 3. Okay, so with that, we're now going to talk about community ecology in the next lecture, and we'll talk about how things like mutualism, parasitism, commensalism, how that affects the relationship between one organism and another in a given environment.